Hello everyone, welcome to our lecture 11 on Mechanics and Materials 1. In this lecture we want to talk about axial loading, and that is essentially corresponding to sections 4.1 to 4.5 and 4.7 and 4.8 of the Hibbeler book. This is our only lecture on chapter 4 of the Hibbeler book. So before I start talking about axial loading, I need to talk a little bit about the so-called Sanbens Principle. And I want to explain that by an example here. So if you think of a vertical bar here fixed at the bottom, and then on top, let's say you apply a force to introduce a tension in this bar to elongate the bar. And if you pay attention to the region very close to the point at which you apply the force, you can see that the force influence is felt by its neighborhood, basically. So if you think of a cross section on top of that bar, you can clearly distinguish between the point at which you apply the force and the edges. If you go further down a little, you see less dominant effect from the location of the force, and the further down you go, you see less and less of that local influence of the force. And eventually, if you reach a certain height, or if you are sufficiently far from the point at which you apply the force, then you see a uniform distribution of internal forces and stresses and strains caused in the bar. The same thing holds for a compression test. So again, if you now compress the same bar, instead of applying a tension load, you apply a compressive load downwards. And if you look at the region close to the point at which you apply the force, you can see a very clear influence of the force exactly where the force is applied. But when you come down, and if you are sufficiently far, then you do not know exactly where the force is applied. So you only see the influence of the force as an average effect. You don't see that strong local effect. Now, you can imagine sort of that if you want to analyze this cross section, this is a very nonlinear problem. It's rather complicated to talk about this in Mechanics and Materials 1. But if you assume that we are always sufficiently far from the point at which we apply the force, then we are dealing with this case of uniform distribution of forces, or uniform distribution of internal forces and stresses and strains, and that's essentially the spirit of the so-called Sanbens Principle. So Sanbens Principle states that stress and strain produced at points in a body sufficiently far from the load is the same for any statically equivalent resultant applied in the same region. So what does that mean? That means if you think of a little specimen like this and you apply a force P, let's say in the middle, now if you cut a cross section below that and close to that point, you see a clear stress distribution which looks like this, indicating that you have more stress in the center and you have less on the edges. And if you cut it a little bit further, you still see the same influence, but much less dominant. And eventually, if you're sufficiently far from the point at which you apply the force, then you just see a uniform stress distribution. Now, Sanbens Principle also states that if you have this case, now instead of one individual force P, if you split that into two forces, P half, such that their resultant force is the same as P, which in this case you can imagine it is, then you also get exactly the same stress distribution as you got before if you are sufficiently far. So you can imagine if you cut it here, that's not the case. So possibly here you would see a stress distribution which looks like this, and if you cut this here, you would see maybe a stress distribution which looks like this. But we don't want to talk about this. We want to talk about cases that we are sufficiently far, and then we can talk about stresses in the sense of a average quantity, and then that stress average is normal force divided by area. And obviously this problem that I'm talking about is about normal forces, but you can imagine the same concept also holds for shear forces and so on. So, but for normal forces, that's what we want to talk about. The idea is that we are sufficiently far from the point at which you apply the force so that you can always talk about the influence of the force as an average quantity, not singular quantities at particular locations. All right, so from now on, we assume that we deal with sections sufficiently far from the point of the application of the force, and in that sense, you can assume that stress is the same as average stress, and that would be force divided by area unless otherwise is specified. Okay, so now equipped with Sanbens principle, we want to talk about elastic deformations of an axially loaded member. So think about a member as shown in the figure that is fixed at the bottom, and it has the height L or the length of L, and on top of that you apply a force P, and as I said, we don't particularly talk about a cross section very close to P. We assume that P has this so-called average effect according to the Sanbens principle. Now, under the influence of P, we will see a change of length delta. So delta would be the change of length of the bar. And assume that the bar has the cross-sectional area A. So we want to analyze this problem, and we want to do it in the spirit of the figure that we have talked so many times about. So let's say the big picture of mechanics. If you remember, we always said we want to find a relation between deformation, here is delta, and loading, here is P. So if we are asking ourselves, what is delta as a function of P? This is what we want to know. Okay, and then for this particular picture, if you remember, we calculated stress in chapter 1. So stress is normal stress now, and that would be P divided by area. So we have stress from what we learned in chapter 1. We have strain from what we learned in chapter 2. So strain is also the normal strain, and that's delta L divided by L. And from chapter 3, we learned that the linear elastic material, or Hookean material essentially, would be corresponding to sigma equals E epsilon, or let's say stress is proportional to strain if it is linear elasticity. Okay, so what we want to do now is to merge all these three equations together, and if you do that, you get this relation. So remember, we were looking for a delta as a function of P, and that's exactly delta as the function of P, the force that we have on top. Now, this delta, or change of length, is the change of length on top of the bar. And then similarly, we can ask ourselves, well, what's the displacement at a certain height, x? So we know at the bottom, delta is 0. We know on top, delta is PL over EA. The question is, what is delta at x. So in order to do that, we need to remember what was the definition of a strain. So the definition of a strain was strain equals change of length divided by length. And now that was for the whole length L, but also it could have been for any smaller length S. So in this case, that smaller length itself, it would be dx. So the change of dx would be d delta, and then dx itself is like the length increment. In other words, you can say d delta is equal epsilon dx. And if you integrate this, you should be able to calculate delta. So that's exactly what we do. So delta at x is the integration of epsilon dx from 0 to x. And then in that relation, you remember that sigma equals E epsilon. So that means epsilon itself is sigma divided by E, and then sigma itself is P divided by A. So we can replace that epsilon here, and you can see that for this particular problem, actually this is a constant. So if you do that, then you get delta x equals Px divided by EA. And then again, remember, if you did this integration, basically you would have delta x minus delta at 0. But in this particular problem, we know that delta at 0 is actually 0. All right, so this is the answer to the displacement at x. And also you can see that if instead of x, you insert the whole length L, you recover what we had before. So basically it tells you that delta is linearly proportional to x because this is constant. But then we want to complicate this picture a little more, and we want to talk about a case where we have now different sections. So here you have 3 sections, so section 1, 2, 3, with different lengths and with different material properties. So section 1 has Young's modulus E1. So this is Young's modulus. So you have different Young's modulus. Cross section and length for each section. But you can imagine that equipped with this form, you can treat each section individually, and you can assume that the total displacement from top to the bottom would be the sum of the displacements for each part. And if you do that now for each part, you use this formula, so you get P Li Ei Ai. And then if you sum this over I, you would get the total deformation delta. So we are going to look at an example using exactly what we learned. Let's say you have a shaft made of three sections as shown in the figure, and each section again has its own Young's modulus, area, and length. You apply a force P, 5 Newton, for instance, here at A. Then you apply 35 in the opposite direction. Then you apply 20 at C, and then you apply 10 at D. So the first thing you need to pay attention to is that when we use the formula delta equals PL over EA, P is an internal force. Okay, so in this case, for each section, we need to find out what is the P in that particular section. And in order to do that, we cut the structure as we learned in method of sections, and we can calculate the P. So if we draw the normal force, let's say versus locations for this graph, we get this. So this is the internal normal force, and then again pay attention to this is internal, and these are points A, B, C, D. If we cut the section somewhere here, so between A and B, we would have a compressive force of 5. So that would be minus 5. And then again, minus, we use it to indicate that it would cause contraction as opposed to elongation of the member or section. Then at B, you apply a 35 Newton force. So that means if I cut it here, I would have a tension of 30 Newton. Okay, so basically it would look like this. If you cut the material, then you have this internal force P, and then you have 5 here, you have 35 here. So that tells you that P must be 30. And then again, if you remember our convention, this is plus 30, indicating that it would elongate the member. Okay, so that's what we get. The internal force between B and C is 30, and then from C to D, it would be 10 because we apply now 20 Newton at point C. But also you could have looked at it from the other section. So if you just cut it like this, and then now you look at that little piece, you have 10 Newton at D. So your internal force P must be 10. And then again, it's plus 10 according to our convention. Okay, so if you do this part right, then the rest is pretty simple. You just need to say, well, the total delta is delta from A to D, or you can say D with respect to A. So you may write it like this. So let's say if this is the x-axis or x direction, now the displacement of point D with respect to point A would be D with respect to C, C with respect to B, and B with respect to A. And we can add those displacements. In this case, due to the numbering that we have, delta B with respect to A would be delta 1, delta C with respect to B would be delta 2, and delta D with respect to C would be delta 3. So if you add them up, and if you include the forces, the internal forces, length, Young's modulus, and area for each section, you get this formula, and that would be the answer to this question, essentially. Okay, so we know what is delta for the length L. We know what is the delta at a height x, and we know what is a total displacement of a material or of a specimen that is made of different sections. So equipped with that, now we want to look at this generic case. So let's say you have this generic case, you have a specimen that has forces acting on it, P1 and P2. And in this case, the two forces may or may not be equal because we may have additional forces acting also, or external forces acting through the body too. And then we have a changing cross-sectional area, but also we may have actually different materials. So maybe the upper part is made of a different material compared to the lower part. Now we want to know, if we had this most generic case, how to calculate the deformation of that sort of structure. And then this is exactly what we do like before. So we would say delta from, let's say, bottom 0 to any length x is the integral of strain over the length. Okay, so assuming that you have that, then for a strain you can put the sigma divided by E, and then for sigma you would put P divided by A, but now you only remember that P itself, E itself, and A, they can all be functions of x. And basically once you do that, you get your delta at L as integral from 0 to L of this expression. And then again, remember, this would be, let's say, mathematically speaking, you should have also this addition of delta at 0. But here, for instance, we assume that delta at 0 is 0 because possibly it's fixed or something like that. But this is rather the change of length from top to the bottom. So the next topic we would like to talk about is the principle of superposition. I try to explain the principle of superposition by an example, essentially. So if you think you have a beam here and you apply a force P1 on that beam, and that force will cause a displacement at the end of the beam, let's call it delta 1. So there would be a bending or deformation of a beam, and you get a displacement delta 1 corresponding to P1. Okay, so let's say this is problem 1. And then we forget that, and then there is this problem 2. So if in problem 2, now you take the same beam, you apply the force P2, then you get a displacement delta 2 at the end of the beam. So here is the question. If we define the problem 3 such that in that problem we apply a force P that is the sum of P1 and P2, could we conclude that delta is also delta 1 plus delta 2? So this is essentially the nature of the principle of superposition. So the idea is to allow us to consider this combined system as the sum of the two systems. Okay, so basically that means we want to superimpose system 2 on top of the system 1. Okay, so if this property holds, then we would say we can use the principle of superposition. And if it doesn't hold, then that means we cannot use the principle of superposition. We can think of the same problem in terms of, let's say, a extension test or an axial loading. That is the purpose of this particular lecture. So if you think of that beam now, and you apply a force P1, as we learned previously, you get delta 1 equals P1L divided by EA. Then you take the same beam, you apply P2, and for that matter, you get delta 2, that is P2L divided by EA. So if you apply the force P, that is the sum of P1 and P2, you can actually say, well, delta would be then P L divided by EA. And because that P is P1 plus P2, that means your delta would be delta 1 plus delta 2. So it turns out that for our particular problem of axial loading, we can apply the principle of superposition. So this is the idea. For axial loading, the way we discuss about it and based on the assumptions that we make, we can apply the principle of superposition. But now we want to know why. So what are the limits of this principle and where we can or where we cannot apply it? So the principle of superposition can be applied if loading is linearly related to displacement. In other words, if you could write displacement as a linear function of loading, then you are allowed to apply the principle of superposition. And this is, mathematically speaking, is actually quite familiar, because if you assume that delta is a function of P, and assuming that the function f is linear, if you remember what was the definition of a linear function, it was exactly that f of ax would be a times f of x, and f of x plus y is f of x plus f of y. So this principle of superposition closely is related to this property. So if you know the displacement is a linear function of loading, then that means if you have loading 1 plus loading 2, the displacement corresponding to that would be the displacement of loading 1 plus the displacement of loading 2. So again, for our particular problem of axial loading, because we know that delta equals PL over EA times L, or if you write it as L divided by EA times P, now you can see that delta is proportional to P if L, E, and A are, let's say, constant. So this would be just a coefficient, and if delta is proportional to P, that means it's a linear function of P. And basically, for that matter, for axial loading, you can use the principle of superposition. The next topic we want to talk about is statically indeterminate axially loaded members. And as we will see, the principle of superposition that we just learned, it comes handy in analyzing statically indeterminate systems. I explained that with an example first. So imagine you have the following structure. There are two springs with the spring constants K1 and K2. And on point C, between points A and B, you apply an external force P. Now the two springs are fixed at B and A using the supports, and that will cause to have support reactions FA and FB. The question is, what are the reactions at A and B? So if we draw the free body diagram for the structure, assuming that the plus direction is as such, for the forces, you get FA, FB on the two ends, and then the equilibrium equation that you have is the sum of forces in the x direction equals 0. So this is a one-dimensional problem, and we have one equilibrium equation here. So the sum of forces in x direction is 0. That gives you Fa plus Fb plus P equals 0. Now, if you look at it, you have one equation, but you have two unknowns, Fa and Fb. So it's a statically indeterminate system by definition, in the sense that our static equilibrium equations are not enough to solve this system. Before solving this system, I want to talk about it a little more from an intuitive perspective. So we don't know what FA and FB are, but you can imagine, for instance, if K1 and K2 are constants and are equal constants, so if they are equal constants, then you can imagine that the two forces at A and B should also be equal. Again, we don't know the answer yet, but due to the particular structure and the symmetry of the structure, you can imagine if K1 and K2 are equal, then the forces FA and FB should be equal. There is no reason they shouldn't be equal. Now I want to complicate this a little more. So let's think about the case where K1 is smaller than K2. Now imagine that point C changes its position by, for instance, delta C. And for simplicity, let's just assume that it's 2 centimeters. So assume that under the influence of force P, point C would move 2 centimeters towards right. Now, what does that mean? That means that the spring on the left side, it would be extended by 2 centimeters. And the spring on the right side, it would be contracted. It would be compressed by the same amount, 2 centimeters. So the two springs have exactly the same displacement. Now, for the same displacement, if you know K1 is smaller than K2, then you can imagine the force that you get at A would be also smaller than the force that you get at B. So K1 smaller than K2, it would result in a force A smaller than a force B. Now the opposite case would be if K1 is larger than K2. And then again, you look at it exactly the same way. So you can imagine that if point C is changing its placement by, again, let's say 2 centimeters, then it means you get 2 centimeter extension here, 2 centimeter contraction here, and you have the same deformation, but now because the left spring is stiffer than the right spring, you would get a larger force on the left side compared to the right side. You may want to compare this example by the common example of two parallel springs. So if you think of two parallel springs like this, K1 and K2, and you apply a displacement on top, and let's call that delta C, and maybe in this case, these 2 points would be exactly A and B, you can see that for the same displacement, you would get different forces in two springs if the constants are not equal. But then the sum of those two forces is always the same as the total force. So this picture in principle is similar to having the two springs in parallel. Okay, so I think with this intuition, you can kind of feel where we want to go. Now, if you compare the spring problem to the axial loading problem, so we want to talk about axially loaded members, you can remember that delta was PL over EA. Now, if we reorder the terms, we get P equals EA over L times delta. Now, if you compare that with springs, you can actually see that the parameter EA over L, it plays like a effective stiffness of the member. Okay, so we can think of this as effective stiffness. So this analogy with the springs is not far from what we want to do with axially loaded members. And also you can imagine, for instance, if you have a one-dimensional structure or if you have a truss member, you can imagine if you want to define some sort of effective stiffness for that, you can imagine if you increase the cross-sectional area or if you increase the stiffness, the effective stiffness of the truss member should also increase. So Young's modulus and cross-sectional area, they make sense to be increasing stiffness when they increase, but also you can imagine if you increase the length of a member, it gets less stiff, it gets more compliant. Okay, so again, if you think of a truss member with a certain length L, and then if you use exactly the same material but now you make it longer, then making a member longer, it gives you less effective stiffness. Making it fatter, it makes larger stiffness, and making it stiffer by increasing the elastic modulus or Young's modulus or stiffness basically of the member, it also gives you a higher effective stiffness. Okay, so you see the analogy between the spring problem and a axially loaded member. So we want to now repeat this problem for axially loaded members and see how we can analyze them and compute their responses. So basically now our problem looks like this. You have two members, and this is a one-dimensional problem, and these are, let's say, axially loaded members. And then again, you can imagine there is like an effective stiffness here, KAC for member AC, and there is an effective stiffness here, KCB for the right member. And if you want to calculate that, it will be EA divided by LAC. For KAC, it's EA divided by LCB or LBC for KCB. And this is assuming that E and A are equal for left and right. Now, for this picture, we want to ask what are the reactions at A and B? So essentially the same question. But we want to answer that from an internal force viewpoint. So we want to think, what are the forces inside the members? Because if you remember, the internal forces were the forces that we used for our axially loaded members to calculate the deformation. All right, so we start exactly like we did before. We just draw the free body diagram, and then you write the sum of the forces in x direction is 0. So you get this equation, Fa plus Fb equals minus P, and that is our first equation. And then again, you can play exactly the same game like we did before. We don't know Fa and Fb because we have only one equation and we have two unknowns. But you can also imagine, similar to the previous case, if point C is exactly in the middle, that means LA and LAC and LCB are equal. So in that case, you sort of imagine that FA and FB would be equal. Assuming that LAC would be larger than LCB, you can also imagine FA would be smaller than FB. For instance, you can think of an extreme that force P is applied right on top of point B. If you do that, in this case, that means the whole length would be LAC. And you can imagine if you just apply the force P on top of point B, all of it would be taken by point B, and then point A would not feel anything. So in the extreme where LAC is much, much larger than LCB, you can actually feel that FB should be much, much larger than A, and then eventually if LCB goes to 0, FB would go to force P. And then the opposite case happens if you think of the opposite case. So basically, if you assume that you apply the force P right on top of point A, that would tell you that LAC is going to 0. So in that case, if LAC goes to 0, so it's much, much smaller than LCB, then FA would be much, much larger than FB. And then you can, for instance, imagine that force at A goes to P. So if LAC goes to 0, then FA goes to P, for instance. You can sort of imagine that. At least in the sense of the magnitude, by the way. You can imagine that there is a minus sign for the P. So, but in terms of magnitude, you can imagine that. Okay, so what we want to do now is to use the principle of superposition and see how principle of superposition can give us an additional equation to solve this problem. So again, remember, it's a statically indeterminate problem in the sense that we have one equation, so we are looking for a second equation. So what I'm going to do here is to remove the support at B and replace it by the force FB that we would have otherwise from the support. Okay, so this is exactly the support reaction. All right, so you can feel that these two systems are equivalent. There is no trick so far. Basically, all we did is to replace the support by a force. But now at this stage, we want to use the superposition principle. Okay, so we can say now this system, which has two forces, it could be considered as the first system, which has only one force P and it has no force FB. So this is system 1 plus or superposed by a second system or to a second system where you have only force FB and you have no P. Okay, so the response of the superposition of the two would be the same as, so if you do superposition of these two, this would be exactly identical to what we would have here. And now each of these systems, if you just look at it, each of these systems are simple. Each of them has only one force unknown. So you can calculate the delta, the displacement for each of them. Now, if you think of the displacement of each of these two systems, now let's say from system 1, you get a change of position for B. And from system 2, you also get a change of position for B. So we call that delta B1 and delta B2. Now, if you add these two, you know that should be 0 because from the original system, you know the point B is fixed. So in principle, this is your missing equation. The missing equation is that if you decompose the system into two systems, and if you add the displacements of those two systems at the support P, those two displacements should add up to 0. Now, it's very simple to calculate the displacements, of course. For the first system, delta B, so delta B1, is the same as delta C because between B and C you have no additional force. So whatever displacement you get at point C, it would be the same at point B. So if it deforms by 2 centimeters towards right, this would go also 2 centimeters towards right. So you don't get additional extension or compression between B and C because there is no force. So delta B1 is equal to delta C, and delta C is P LAC divided by EA. Okay, so remember our formula is delta equals PL over EA. That's exactly what we do. So that's delta B from system 1. From the second system, delta B would be force, FB, times length. Now it's the total length divided by EA. Okay, so basically this is sort of what you have here. You have now delta B1, delta B2, you insert them into the geometric constraint of the problem, and then you get this equation. And then again, this equation is equivalent to this one, so it's sort of the same equation in disguise, but now we like this equation better because it's just in terms of forces, and it looks very familiar to the force-related equations that we are looking for and we usually have between the forces. So now you have two equations, two unknowns, and you can solve FA and FB. So in summary, this is what's happening. You have the yellow system, which is our original system. So you have a bar, you apply a force P somewhere between A and B, and you want to calculate the reactions at A and B. Now, you know delta B is 0. That means if you decompose the system into these two systems, and if you calculate the displacement for each of them, the sum of those displacements must add up to 0. You put all these together, then you get an equation. So this is your red equation. And you had the green equation. Now you have two equations, two unknowns. And if you solve for FA and FB, you end up with this relation. So FA would be minus LBC divided by L times P. FB is minus LAC divided by L times P. Then again, pay attention to the minus sign. Minus sign basically tells you that the forces that we had, it should be in the opposite direction, which maybe you could sort of intuitively imagine this should have been the case. The other thing is that what I just said previously, so you can imagine that if force P is applied right on top of point A, then in that case, LBC would be the total L, and you can sort of see the same thing, that if LBC is the whole L, this is the same as if LAC goes to 0, and this gives you FA is the same as P. Well, in magnitude, again, you have a minus for the direction. Okay, so this was something that intuitively we sort of expected. But also, if you divide these two relations by one another, you also get this maybe more intuitive relation. So you would see FA over FB, so the ratio of FA to FB is the same as LBC over LAC. In other words, FA times LAC is equal FB times LBC. So it means that if the arm, so let's call it the arm for A, this is the arm for B. If the arm is longer, the force is smaller. If the force is larger, the long is shorter. Okay, so the arm times force must be equal. And then again, also this relation sort of tells you that if point C was exactly in the middle, then LBC and LAC would be equal, and that tells you FA and FB would be equal, which is another thing that we expected intuitively. Okay, so this is sort of the relation you want, and this was all an example of how to handle statically indeterminate systems. So whenever you get a statically indeterminate system, you should always start with your free body diagram and the common equations of static, like equilibrium equations that you have. And then you always need an additional constraint. In this case, it's a geometrical constraint. So, or it came from a geometrical constraint. At this point, you just see it as forces, so you don't see the deltas anymore. But remember, the reason that this equation exists is that we had a geometrical constraint to the problem. So for different problems, you may need to be using different ways of introducing and finding these geometrical constraints. But long story short, you always have your equilibrium equations, and if they are not enough, you have a statically indeterminate system. Now, for a statically indeterminate system, you should be looking for additional constraints, or let's say geometrical constraints, to solve the problem. We will look into an exercise now, and we better understand this from a different perspective. Exercise 1 of today's lecture is similar to problem 4.6 on page 143 of the book. The three steel bars shown in the figure are pin connected to a rigid member. So we have these three bars that are connected, and they are pin connected to the rigid member at the bottom. If a load of 15 kilonewton is applied as shown, determine the forces developed in each bar. So we have three bars, A, B, C, D, E, F, and you are asked to calculate the forces, the internal forces in each bar, if we apply a force of 15 kilonewton here. And also the cross-sectional area of the bars are given. So bars A, B, and E, F each have a cross-sectional area of 50 millimeters squared. So A, B, and E, F, they have identical cross-sectional area, and that is 50 millimeters squared, and bar CD has a cross-sectional area of 30 millimeters squared. Okay, so as always, we begin with the so-called free body diagram and write our common equilibrium equations. Now, in the free body diagram, you have a 15 kilonewton force downwards, and you have FA, FC, and FE upwards, assuming that these are the three forces here, and these are the same as or essentially they correspond to the internal forces of their corresponding member. So if we can calculate FA, FC, and FE, we know the internal forces that we are looking for. So the equilibrium equations are the sum of forces in the y direction is 0. So assuming that the plus direction is upwards, so you get FA plus FC plus FE minus 15 kilonewton is 0. And then you write the sum of moments with respect to any point to be 0, assuming that counterclockwise is positive. So let's say here, if you write it with respect to point C, then from point A, you get a clockwise moment. So that would be the distance, 0.4 times FA with a minus. From the 15 kilonewton, you get a counterclockwise moment. So that is a plus sign. So that would be plus 15 times 0.2. And from FE, you also get a counterclockwise. That's also a plus. So plus FE times 0.4. Usually, you also have some of the forces in the x direction is 0, but here we have no forces in the x direction, so we don't write it. All right, so these are our common equilibrium equations. Now, as you can see, we have two equations and we have three unknowns. So basically, it's a statically indeterminate system. But it's different, but it's also similar to the previous statically indeterminate system that we had. So as I mentioned before, statically indeterminate systems are very, very different. But in nature, what we do is always similar. We are looking for geometrical constraints to solve these type of problems. Now, what is the geometrical constraint in this problem is the fact that the member here, the blue member here, is a rigid member. So It's rigid in the sense that it's not going to deform, it's not going to deflect under loading. What does that mean? That means if at the beginning it's a straight rectangle like this, it would be a tilted rectangle like that, but it remains exactly a rectangle as it was before. So this property, it gives us some idea about the relative deformations of the points A, C, and E. So we don't know what is delta A, okay? We don't know what is delta C. We don't know what is delta E. But what we know is that they deform such that the member remains rigid. In other words, we know that if you think of this triangle, this would be similar to this smaller triangle inside it. Okay, because the angle is the same angle. Or in other words, if you calculate the distance here, so if you call it, let's say, h, w, h divided w here is the same as h divided w here. So more specifically, if we call this distance delta c and we call it this one delta a, then delta a minus delta e would be this height, the difference here. And if you divide that by the length 0.8, it would be the same as this little distance, which is delta c minus delta e divided by the length 0.4. All right, so this is in principle our third equation, or otherwise it's our geometrical constraints. It's our geometrical constraint that we were looking for. Sometimes you may have multiple constraints and then you would be able also to employ them if it is necessary. All right, so if we play with the terms a little, we come to this relation. It's essentially the same relation, and as I said, it's our third equation, but it's sort of our third equation in disguise, because you cannot use that immediately together with the previous equation. So what we need to do is to rewrite these deltas also in terms of forces. So if we can express the delta C, delta A, delta E in terms of forces, then we have our equation, and that's fairly simple using the formula that we had for axially loaded members. So again, you remember delta is PL over EA in principle. So this is our generic form. In this case, it means delta C is FCL divided by EACD. So all the three members, they have the same length and the same material, but they have different cross-sectional area. But in principle, you may also have problems that they have different materials. Okay, so if you replace the corresponding deltas in terms of F's, then you get your third equation in terms of F. And now this is exactly what you wanted. So you have now equation 1, 2, 3, three equations, three unknowns, Fa, Fc, and Fe. And using the three equations, you can calculate the three unknowns, and you would see Fa is 9.52 kilonewton, Fc 3.46 kilonewton, Fe 2.0 kilonewton, and then remember that we have drawn the forces like this. So that would naturally mean that the force in the members, so in each member, if you, for instance, if you think of a member like this, and you have this force upward at the rigid member at the bottom, then that means you have the reaction of that acting to the bar itself. So the internal force of the bar is obviously the same as the force that we used. Okay, so this means all the bars are under tension, and we have actually used that principle here. So it's sort of important that if you look at FA, FC, FE here, these are the forces acting on the rigid member. But when you use them inside the equations that we had for axially loaded members, these are now considered such as internal loads. Okay, so this duality between being external, internal, you should always pay attention to. All right, so this is another example of a statically indeterminate system. And if you compare this with the previous example, you sort of realize that they have similarities and they have differences. And in principle, always what you need to do is to find equilibrium first, and then you want your constraint second. And once you have the two of these, you should be able to handle these types of problems. So you have equilibrium and constraint. These are the two ingredients of solving statically indeterminate systems. The next topic we want to talk about is stress concentration. Now think of a member as shown in the figure, on which you apply the normal forces P in two opposite directions to cause a tension in the member. Now this is a uniform member with cross-sectional area A. That means if you cut this member at any section, and if you look at the distribution of the stress inside the member, you would always see that the stress distribution is uniform, and this is normal stress, obviously, because we are talking about axially loaded members. So in this case, the stress distribution is uniform and is obviously equal to the average stress. And that would be the total normal force divided by cross-sectional area A. However, if we compare that with a slightly more complicated geometry, so let's say you have a plate with a hole in the middle. Now, if you apply the same forces, so the same normal forces to the plate, you can imagine that if you cut this at two different cross sections, AA prime and BB prime, you may see different stress distributions. And we want to talk about that. So if you cut it at a cross section BB prime, and then again imagine that we already are sufficiently far from the point where you apply the force P, so we follow still the so-called Sanbens principle. So if you cut it at a cross-sectional area BB prime, then you would see a stress distribution that is uniform, and the value of that is the normal force divided by the area of the cross-section, or cross-sectional area ABB prime. But if we cut it at a cross-section AA prime, a more complicated picture will appear. So what we will see is that due to stress concentration, you would get more stress closer to the hole, and you would get less stress further at the edges. So this results in a maximum stress and minimum stress in your stress distribution. And then obviously when you have a mean and max stress, then you also have an average stress somewhere in between. But this is also important that the average stress here is not the same as the average stress at BB prime, because you actually have a smaller cross-sectional area. So if you think of this example, as we said, for cross-section BB prime, the average stress is force divided by cross-sectional area ABB prime. Whereas at AA prime, the average stress is force divided by cross-sectional area AA prime. And because A prime cross-section is smaller than BB prime cross-section, then the average stress here is larger than the average stress at BB prime. Okay, so that's one thing. So the average stress itself is higher, but that's not the whole story. Even that average stress is smaller than the maximum stress that occurs in that particular cross section. So you should always think of it this way, that there must be this equilibrium, and then equilibrium means that you should have the same P here and you should have the same P here. So, and you know that P is the integral of stress dA. So because at AA prime, the area is smaller than BB prime, the average stress that you get is larger. But also, as I said, that's not the whole story. The more interesting story is that there is still a maximum stress that is even higher than that average stress. So you can imagine in terms of material design, and for us, this is very important to distinguish between this stress and this stress and this stress. And obviously the bottleneck in this case is the maximum stress. So that brings us to the context of stress concentration and stress concentration factor. So you define this factor K, and we call that stress concentration factor, and that's the ratio of maximum stress by average stress. But then again, I repeat that the average stress is the average stress in that particular cross section, which is possibly higher than the average stress in other cross sections. And as I said, we are interested in maximum stress, so this is important for our design criteria. Now, talking about the stress concentration factor K, you can imagine this is a number that is always larger than 1. So in the limit is equal 1. But it depends on geometry and loading. Okay, so for instance, if you think of a plate with a hole, or if you think of a sample with different cross-sectional area like this, you can imagine that you get different stress concentrations. But also you can maybe imagine that for axial loading, for torsion, and for bending, you would have different distributions of stresses. Okay, so it depends on geometry and loading, but maybe also you can imagine that in general, it should not and it does not depend on material nor the magnitude of loading. So we assume that if you change your loading, whether you apply 100 Newton or 200, we are dealing with the same problem. Also, we assume that if you deal with different materials, it doesn't change the stress concentration factor. So stress concentration factor is a value that is usually calculated analytically and sometimes with computational simulation, but it's a function of geometry and loading, and this nice property allows us to basically tabulate it. So we can have tables of stress concentration factor for each geometry and loading type, and then you can apply that to any material and magnitude of loading that you want. So if you have problems that deal with the stress concentration factor, you have these 3 steps. Step 1, you need to read that stress concentration factor for that particular geometry and loading from handbooks or tables that you are given. Step 2, you compute sigma average. And then again, for computing sigma average, you should be careful of the area of the cross section that you choose. Step 3, you calculate the maximum stress based on that average stress and by multiplying it by stress concentration factor. So that's all you have to do. Now, an example of a stress concentration factor table or graph is this. So for instance, if you have a plate with a hole like we just discussed about, you can see that the cross-sectional area here is W times T. So W being the, in this case, height or the width of the sample, T is the thickness. But you will see that when you want to calculate the average stress, you divide the force by the area of that particular cross section. So sigma max would happen here where you have the smallest cross section. So you're actually calculating the stress concentration factor for that particular value. And you can see that if 2R over W is increasing, stress concentration factor is decreasing. And if it comes to 0, then you come to the limit 3. So this limit 3 is very interesting from, let's say, mathematical perspective, and it's indeed an analytical solution. So basically it tells you if you have a very, very tiny hole in the material, you get 3 times more stress around that point compared to the rest of the material. Okay, so this is essentially what it is. Then you can also think about this other geometry, and here if you think that R is this fillet radius sort of, and you have W, this is the width of the larger part, and then H is the width or the height of the smaller part. So again, in this case, when you want to calculate the sigma average, the stress average, you divide the force by the smaller area, so HT, and then for each ratio of fillet radius divided by H, you get a different stress concentration factor, but also you can imagine the ratio of W over H is changing this problem. So the important thing here is that you can see that, for instance, if R over H goes to 0, that means you have a very, very sharp corner. The stress concentration factor goes to infinity. Okay, so this property that if fillet radius goes to 0, stress concentration factor goes to infinity, it tells us that we should avoid sharp corners in design. Okay, so if you want to design something, the first thing is to avoid sharp corners. Another thing is that you can see that if the ratio between the two parts W and H increases, the stress concentration factor, sorry, if the ratio between W over H increases, the stress concentration factor also increases. And that sort of makes sense because you can imagine in the limit when W over H is 1, this would be just a uniform sample, so stress concentration factor should be 1. Okay, so if W over H is 1, then you should just get the horizontal line. All right, so basically you have these sort of tables and graphs, and from that you can calculate the stress concentration factor, and as I said, you calculate K, you calculate sigma average, and from that you can calculate sigma max, and that is what you use for your design, for your design criteria. The next and last topic that we want to talk about in this lecture is inelastic axial deformation. Now, assume that we are dealing with a ductile material that is elastic perfectly plastic. So we talked about this term previously, elastic perfectly plastic. It means that the material behavior consists of two parts. You have the elastic part, that is linear elasticity, until you reach the so-called yield stress, and after that you have a constant stress, and basically the material yields. Now, we want to combine this concept together with what we just learned from the stress concentration. Now, think you have a member like this, so it's a plate with a hole, and you apply a force P at the two ends of the specimen. Now, for a value P1, let's say if we apply that force P1 and we cut the specimen in the middle, now cutting the specimen in the middle gives us the stress distribution on that particular cross section. And as we spoke previously, you get more stress closer to the hole and less closer to the edge, and then you get a distribution between them. All right, so if P is not large, so if this P1 is not too large, then the stress that it causes in the material, even the maximum value of that stress, would be less than yield limit. Okay, so this is for a P1 that is not too large. Now let's say we increase this to P2 such that we just reach exactly the yield stress where the maximum stress occurs. So that means up to this point, the deformation would be completely elastic. In other words, it means this limit would be your maximum elastic load. And for that maximum elastic load, PE, you know sigma y divided by k times a holds. Or in other words, you can imagine that the yield stress in this case would be the maximum stress. Now maximum stress is stress concentration factor times average stress, and that would be stress concentration factor times PE in this case divided by A. Okay, so this is what it is. So this is the maximum elastic load in the sense that your maximum stress just reaches the yield stress. But now if you increase P further, the maximum stress cannot exceed the yield limit. So remember, the yield limit, according to elastic, perfectly plastic material behavior, is the maximum stress that you can achieve. So basically what it means is that if you further increase the force, what happens is that you get this sort of flat area of stress, and then you get the rest of the distribution. So this is sort of an intermediate step until you reach the upper limit, and the upper limit is where the whole stress distribution is just uniform and is yield stress. In this case, sigma max equals sigma yield and is equals sigma mean. So this was sigma max equals sigma y, that was the elastic limit, but if sigma max and mean are equal to sigma y, then this is your plastic limit. So this is your maximum plastic load. And for maximum plastic load, the force P is sigma y times A, because the stress is just uniform, and that uniform stress is sigma yield. That would be your relation. And if you compare this relation with what we had here, you can actually see that maximum plastic load is equal to stress concentration factor times maximum elastic load. Exercise 2 of this lecture is similar to problem 412 on page 167. The bar in the figure is made of steel and is assumed to be elastic, perfectly plastic, with yield stress of 250 megapascal. Determine A, maximum P without causing the steel to yield, and B, maximum P that the bar can support. The dimensions are given here. So the width here is 40 millimeter. The thickness in the other direction is 2 millimeter. And the notch radius, the fillet radius sort of here is 4 millimeter. Okay, so the first thing we want to do is to calculate the stress concentration factor. So if you remember, for this type of structure, we had W as the width or height of the larger part, and then we had H as the height of the smaller part. So in this case, H would be 40 minus 2R, that's 32 millimeter. Then R over H, that would be the radius here, times H, is 4 divided by 32, so that's 0.125. And W over H is 40 divided by 32, that's 1.25. So from these dimensions, we can come to the table that we have, or to the graph in this case that we have. You find the corresponding values for W over H, for instance, R over H, and you calculate the stiffness, the stress concentration factor. So here we have the line for W over H 1.2. We don't have exactly 1.25, but we can imagine that if we take the 1.2 line and we go slightly further up, it would work. For R over H, 0.125 would be somewhere here. So from this, if you intersect 0.125 with W over H 1.2, you get 1.7. And if you go slightly higher, we get 1.75, because W over H is slightly higher than 1.2. Okay, so we pick stress concentration factor to be 1.75. Then you calculate the average stress. Sigma average is equal P divided by A, and sigma max would be K times sigma average. So for part A, we are looking for a maximum stress, or we are looking for the maximum elastic stress. So there is still a stress distribution here. So if you assume that maximum stress is equal yield stress, remember that was our condition for maximum elastic load, then you just insert maximum stress from this relation. Sigma y is given. You know the stress concentration factor from the previous graph. So you put all that together and you can calculate maximum elastic load, and that would read 9.14 kilonewton. So that means if you apply a force 9.14 kilonewton, this stress distribution that you have here, it would be such that the maximum stress would be equal to the yield stress, and the rest of the distribution is less than the yield stress. So until this point, it's purely elastic. Now for the next part, for part D, you are asked to calculate the maximum force that this member can support. Now the maximum force is like maximum plastic load. So basically, this is the load that when you apply, the whole cross section becomes plastic, or it behaves like a plastic material, and you cannot go further than that. So in that case, the stress is just equal sigma y, and stress is P divided by A, and that is sigma y, and it's a uniform stress, so it doesn't have max or min anymore. And if you insert the numbers, then you get maximum plastic load to be 16 kilonewton. And then again, remember we had this nice relation. We said maximum plastic load would be stress concentration factor times maximum elastic load. So you can also check that, and that holds. The third and the last exercise of today's lecture is similar to problem 413 on page 168 of the book. The rod shown in the figure has a radius of 5 millimeter and is made of an elastic, perfectly plastic material for which yield stress is 420 megapascal and elastic modulus or Young's modulus is 70 gigapascal. If a force of 60 kilonewton is applied to the rod, as shown in the figure, so this is the force P equals 60 kilonewton, determine support reactions and stress in each section. All right, so we draw the free body diagram as we have done in the previous problems. So we don't know the reactions from the supports. We draw them as FA and FB. And then we apply the force 60 kilonewton towards left. Then we write the governing equations or the equilibrium equations. The only equilibrium equation we have here is the sum of forces in the x direction is 0. So that's what you can write. And that gives us FA plus FB minus 60 is 0. Now, this is obviously a statically indeterminate problem because we have two unknowns and one equation. So we use our relation that we derived previously for a similar statically indeterminate system. Okay, so if we use that, then we will see that FA would be 45 kilonewton and FB would be 15 kilonewton. And that sort of makes sense because if you look at the distances here, this is 300 millimeter, this is 100 millimeter. So because the length BC is 3 times the length AC, we expect the force in AC to be 3 times the force in BC. All right, so this would have been the answer to the problem if it was a purely elastic problem. So if it was just a elastic material behavior, this is what we would have and we would be done. But that's not the case. So we need to make sure that the stresses that are caused by these forces in these sections, we need to make sure that these stresses are less than the yield stress. And that's what we want to do now. So if you calculate the stress in section AC, that would be the force divided by area. Area is pi r squared and r is 5 millimeter. The force is 45 kilonewton. So you get the stress of 573 megapascal, and that's the compressive stress. So you can tell from the sign of A. So this section AC would be under compression with the stress of 573 megapascal. Now we play the same game for the next section CB. The stress in CB would be the force 15 kilonewton divided by the area, and that would give you 191 megapascal. So it would be 1/3 of what we had previously. But now pay attention that this time it's tension. So it was compression in AC, it's tension in BC. Okay, so what we need to do now is to compare these with yield stress. And the yield stress is given to be 420 megapascal. That says the maximum stress that we can have in AC would be 420 megapascal. So essentially, if you think of a material behavior like this, what we calculated, that's 573, it would be somewhere here. So it's like a linear extrapolation of what could have happened, but that can never happen because at 420, we need to cut the stress. That's the upper limit for the stress. Okay, so basically that tells us that in member AC, the stress that you get here is not valid. The stress would be 420 instead. And knowing that, we need to sort of come backwards and recalculate the force itself. So if we know the stress is 420 megapascal, which is the yield stress, now you take that stress, you multiply it by area to calculate the support reaction. And that would be 33 kilonewton. So the force in member AC, it is not 45 kilonewton. It's rather 33 kilonewton. So this is the maximum force it can carry. So it cannot be more than 33. So if that is 33, then how much would be the force for BC? That would be then 27 kilonewton. So remember, we have this equation. So the sum of the two forces should be 60 kilonewton. And now because you know FA is 33, you know that FB would be 27. So considering that FP is 27, then the stress in CB would be 27 divided by area, which is 344 megapascal, and that is less than yield stress, and that is valid. So that tells us that the 191 megapascal that we calculated previously is also wrong. Okay, so the answers are here. Basically what we had previously, it was a trial step, and due to the material behavior, they are not valid. So the support reaction at A is 33 kilonewton, at B is 27 kilonewton. The stress in AC is 420 megapascal, in BC is 344 megapascal. These are the final and correct answers. All right, this was our lecture on axial loading. We covered sections 4.1 to 4.5 and 4.7 and 4.8 of the chapter 4 of the Hibbeler book, and that was our only lecture on the fourth chapter of the Hibbeler book. I'll catch you in the next one.